easier for me. So I'll try to be like as clear. I'll be try to be very clear with all the problems. So, but if like any one of you has any questions at any stage, please feel free to ask. So you can just like unmute yourself and ask a doubt if you have any at any point. I'll not be keeping up with the chat generally, so unmuting yourself would be the best thing. Okay, so yeah, let's move on to the problem. So like you'll see like a lot of like ideas from the proofs in which we saw in the last class are going to be used in this problems, and uh, we'll see a lot of interesting ideas as we go through the solutions. And apart from that, I just want to make it clear like all the problems in the set were very hard. As in, extremal graph theory is a kind of topic which, like, if it comes in an Olympiad, it is going to come as it mostly comes as like hard end problem 3 or problem 6. So it's okay if you were not able to get any of the problems. They were like last 5 problems, all of them were TST level. The first 2 were kind of classic, but they are still hard, and last 5 were really hard. Okay, so like let's start. So the problem one is problem one tells you that prove that if a graph has 2n vertices and n square plus 1 edges, then prove that it has at least n triangles. So this is actually a theorem, and this is called Rademacher's theorem. So we'll start with the proof of this. So did anyone have any ideas on this? Also, maybe today I might take a bit longer than 90 minutes because I want to discuss all of the problems. Okay, let's see. Anyway, yeah, does anyone have any ideas for this? How to begin? Okay, so first of all, obviously, we'll try to understand why the problem is true, right? So note that the Turan's theorem tells you like, if, not Turan here, Mantel actually. So Mantel basically tells you that if V is 2n, then max edges to avoid a triangle is what? N squared. So this problem has one more edge. This graph has one extra edge. So if you like draw the equality case for Turan and then compare it, how does it look like? So for Turan, you draw something like this, right? So we are suppose we have 2n equals 6, then you are drawing a k3 comma 3 with an additional edge. So suppose this is your k3 comma 3. Okay. Suppose this is an edge, this is an edge, this is an edge. Okay, the boring stuff. Okay, and suppose the extra edge is this. So you can see like why the problem is true, right? So suppose if this was 1, 2, and 3, and this was 4, 5, and 6. So you have triangles 1, 5, 2, I think, yeah, 1, 6, 2, and 1, 4, 2, right? So this problem is true. That's okay. That is something we need to understand first. So does anyone find any claim like from the equality structure in general? So this is kind of the optimal case scenario, right? And I'll just do something else. I'll write the degree of every vertex next to it. So this vertex has degree 4.
There will be a vertex V whose degree will be lesser equal to n.
Okay, yeah, let's see. Okay, let's do that. Okay, this is also 4 actually. Sorry, this is 3. Whatever I write in violet is the degree of that vertex. Is less than or equal to n. Okay, that is a bold claim, but I think that is also true. Yeah. Okay. We can actually use something stronger. I think maybe we could do something like this, but maybe we can use something stronger. So one idea for the solution is obviously we are going to induct, right? Because induction is something that is very like looks feasible in this problem. Why? Because like again, like we said at the start of the lecture, like previous lecture that induction is particularly good with graphs because like if you delete a vertex of the graph, it's still a graph, right? And if you delete an edge, it's still an edge. So you can try to think about inducting somewhat like you can go from, you are inducting on n obviously, so you can go from like 2n to 2n minus 1 and n squared plus 1 to n minus 1 plus n minus 1 whole square plus 1. So can you think of a deletion of something that can bring about this? This is one way to think about it. Another way is to like directly guess a claim from the optimal structure. Do you see something about, okay, like take a look, like obviously 1 and 2 is very special, right? So can you say something about, because they have the extra edge in the optimal graph. So can you say something about degrees of 1 and 2?
They have the degree greater equal to n, greater than.
Greater than n. Okay. Okay, so
That difference is at most 0 or greater than 0 if any extra edge is there between another vertex.
okay, so something, are you saying something like this? If UVW is a triangle, then degree U minus degree V is at most 1, something like that?
Yeah, maybe
Okay.
like the difference is less than or equal to 1.
Okay, so think about it, like you have to induct, right? So somehow you have to delete two vertices such that this happens obviously and this happens. So think about it like this: you have to delete the vertices in such a way such that you are deleting something like at most two n edges. Can you do something like that? Because like okay, like the problem is for g with v equals n and e equals n squared plus 1, sorry, v equals 2n and e equals n squared plus 1, right? Obviously the problem would be true if e would be at least n squared plus 1, right? Because adding more edges does not like give you any harm. It will only result in the possible addition of more triangles and it will like not affect the main triangle value. Okay, so whatever, so like just think of a way to delete two vertices u comma v that will delete like two n vertices, sorry, two n edges. So actually, the claim I'm hinting here at is kind of stupid because you kind of need to have this idea in mind that I'm going to induct at the end of the day. So you can basically see if you have any triangle, let's say 1, 2, 4 is a triangle. So the sum of degrees of 1 and 4 is what? 7, right? 7 is greater than 6. Similarly, 8 is greater than 6 and 7 is greater than 6. So like the main claim is if, okay, just write it with, oh, I'll write it with a different color maybe. Okay. Main claim. Oh, if
We
UVW
can
is a
just
triangle,
the vertex p whose degree is lesser equal to n.
yeah, but that deletes only one vertex, right? So you are going from 2n to 2n minus 1. That doesn't really help with induction. And you're going from n squared plus 1 to like at least n squared plus minus something like that. Doesn't really help with induction. For induction to be carrying out, so for you to carry out induction, you need to delete two stuff. Yeah, so that is the idea. So suppose basically the claim from here is like if UVW is a triangle, and you know that such a triangle, and I know that such triangle exists by mantle, right? Because you have one extra edge in other, like you have an extra edge than what mantle tells you can have. So if UVW is a triangle, then degree U plus degree V is at least 2n plus 1. Why is this true? Because if the degree was less than 2n, like at most 2n, right, you can delete UV. So the resulting graph, suppose G1 is the resulting graph, which is like you find it by deleting UV, has 2 times n minus 1 edges, not edges, sorry, 2 times n minus 1 vertices, and at least n square minus 2n plus 1, that is what? N minus 1 whole square by 2, or n minus 1 whole square plus 1 edges. So you can carry out an induction on this. So by induction hypothesis, G1 has n minus 1 triangles right? And UVW is not one of them because, well, G1 does not have UV. So add in UVW and win. So this was the main claim for the problem. If you have UNV UVW forming a triangle or an edge UV a part of a triangle, then this degree condition must hold. So this is the main point of this is the main claim basically. How do we get at this claim? This is partially motivated by the optimal structure where you see that this is, first of all, this has to be true, right? And second, we are thinking inductively. We are always trying to like remove two vertices and remove, well, in other words, not too many edges. You need to remove two vertices and you need to ensure that their combined degree, or in other words, you are not removing too many edges. If you remove too many edges, you cannot carry out induction. Okay. So someone suggested removing one vertex. One reason that does not work is you are going from 2n to 2n minus 1. So it doesn't help with the induction. Okay. So, okay, let's move to the next page. Page after. So what this tells you is basically you have degree u plus degree v is at least 2n plus 1, right? And this is also true for v and w, right? So summing up cyclically and dividing by 2, this is going to give you degree u plus degree v plus degree w is at least 3n plus 3 by 2. You just do the sum yourself, okay? Now, these are integers, right? So doesn't make sense to write a fraction in here. So this is basically telling you degree u plus degree v plus degree w is at least 3n plus 2. So now, like think about it. I'm telling you, like if UVW is a triangle, then the sum of their degrees, like they give out a lot of edges basically. Three n plus 2 is a lot of edges because you have like what 2n minus 3 remaining vertices, right? So something like, suppose A was a vertex not in UVW, right? UV and so suppose you had like suppose let something like, let's say x of A denotes how many neighbors A has. We say that a vertex is a neighbor of another vertex if it is connected to it by an edge. Okay, so how many neighbors A has in UVW? Right. So whenever XA is greater than equal to 2, this gives you a triangle with edge UV, not UV, edge in UV or VW or WU, right? Which is not UVW. Or let's say F of A instead. That would be better. So now think about it. So suppose you know that there are 2n minus 3 vertices, right? So and you have like 3n plus 2 edges. The sum of their degrees is 3n plus 2. So now you can kind of end by pigeonhole. I'll leave the proof to you guys, like because this, basically the argument carries out like because 2n minus like, okay, yeah, I think the argument carries out that where is the eraser? So from here you can basically use pigeonhole or something to show that at least like n minus 1 guys out of say UVW, like in let's say write it like this. So n minus 1 guys inside this set set minus UVW have the F value like greater than 2. So this basically finishes. So I'll leave the proof to you guys. This is not very hard. You can just use a PHP argument. Basically, the idea was that you have like a lot of edges coming out from a triangle, like the vertices of a triangle. And so that is going to give you like So you can basically, and at the end of the day, like prove something like all the triangles will have an edge between UV and VW and WU. This is also kind of motivated by the equality case because, as you note, like, well, so all the triangles have like the 1-2 edge, right? You can also draw some other examples. You'll find that this holds. So that might be another motivation for it. So yeah, this was all about the first problem. Does anyone have any questions? I'm audible, right?
Yes.
Yes, yes.
Okay, okay, cool. Okay, I'll move on to the next problem. Guys, feel free to ask questions if you have any. Okay, I'll move on to the next problem then, I guess. So the next problem is like, so you're given like non-negative reals xi, I equals to 1 to n, are assigned to vertices of a triangle, of a, sorry, not triangle, of a graph G. It is given the sum of all the xi's are 1. Find the maximum value of uh, okay, find the maximum value of UV edge xu times xv for given G, let's say. You can do it for a given G and then just extend it to like all possible graphs G with vertices and n vertices. Yeah. So does anyone have any ideas for this problem?
UV in edge, and then the graph, is the graph connected or incomplete or something?
No, like in general, the graph can be like any general graph on n vertices.
Okay, so it is over all graphs, right?
Yeah, you can like think about it like that. You can find the maximum value for a given graph G, and then like for or across all is just easy from there, right? Just plug the value or something. You'll find it as a function of n. So the maximum value for any should be like, yeah, you can just find it for any arbitrary graph G on n vertices and then like extend it to all. So like first
N
of all,
minus 1 by 2n.
right? Yeah, that is correct. Okay, so the n minus 1 by 2n is for like I think it is for kn, right? Yeah. So this is a
Yes,
good
for complete
st-
graph.
yeah. So this is a good starting point. Uh, that is calculate the value, calculate for kn, right? So how do you think about like kn? So for kn, the sum is like just uv belongs to e xu xv. I think it's something like just half of summation xi whole squared minus summation xi squared, right? Which is 1 minus this thing. I'll just not write it, I'm lazy. And then you can just cs it or something, 1 minus 1 by n, right? So this is a value. So this will tell you for the kn. So now how do you do this for the general case, right? Because we did not solve the problem, right? We just guessed the answer sort of. So how do you do it for a general case? So like if you think about it, in kn case, all xi were equal. Like, so we can guess that in general case, xi's should be kind of equal. Like, okay, this is vague, should be some kind of equal to each other. What I mean by that is, let's say it would be something like, suppose your graph G had a maximal clip KR, right? Then maybe something like, uh, let's say xi equals to 1 by r, where I is at most r, and xi equals to 0 if uh, it is the other vertices. So what I just did here is I'm taking a guess. We saw that for the kn case, if xi's were all equal, that gives us like the maximum value. What I'm thinking something is like, if suppose G has a maximal click, that is kr, right? So what we do is assign the vertices of the kr as a given value, that is like 1 by r, so that the values assigned to the kr are the same, and assign 0 to all other values because we need to keep the sum, right? So we guess that the answer should be something like this. But now, how do you prove this? So any ideas?
Can you again repeat what you said about xi equals 1 over r and xi equals 0?
Okay, so basically for the kn case, what are we doing? Like, what is the equality case for kn? All the variables are equal, and all the variables are equal to I by n, 1 by n, right? So here xi equals 1 over n for all I, right? So this is what we are doing for the kn case. So we take a guess for a general graph G. What will happen is, like, suppose G has a click R click embedded inside, right? R click is a complete
Oh,
graph on
okay,
R
got it.
vertices. Okay. So then what we are doing, like, we
Okay, yeah.
guess that the answer should be something like it's equal for all vertices of the R click, and it is 0 for all the vertices of other the other vertices, because we need to maintain the sum 0. Summation xi should be 1, right? How do you prove this? So what we will do is, like, this is a smoothing argument. So this is a smoothing argument. So note that in the like alleged equality case, we have a lot of variables 0, right? So we will try to show, say, suppose like something like G is okay. Suppose, okay, no, sorry. Uh, uh, Suppose like you have u comma v is not an edge, right? And xu and xv are both greater than 0. Then shifting xu xv, shift one of them to 0 and the other to their sum. This doesn't decrease the f value. Okay, what is f? F is basically f of x1 x2 up till xn is basically just this
The
thing.
sum.
Okay, yeah. Just write it out for the sake of clarity. So this is a smoothing argument. So now, how are we supposed to execute it? So, like, just writing out everything is going to be messy, right? And tackling it might be hard. So what we are going to do is we'll appeal to extremal principles. So what we will do is, given G, take x1 comma x2 comma such that f of that thing is maximum. Okay. Okay. So now you know that you have a tuple x1 up till xn such that f of that is maximum. So what we will do is, like, this is basically how smoothing works. If people do not know about smoothing, they can read about it online. There are a lot of resources available, but this is how smoothing basically works. You prove that you can bring two unequal variables closer to each other or something like that, or you can, like, read it closer to each other. This is one thing to do. This is a sort of smoothing which works like this. And there is another sort of smoothing is, like, you can decrease one variable and increase other without disrupting anything. So in both cases, keep that in mind. You can't disrupt anything for bad or the worse, yeah, without disrupting anything. So this is the xy to 0 comma x plus y type of smoothing, right? This is what we are going to do actually here. Okay, this is what we are going to do. So now think about it. We are given, suppose we take a tuple x1 up till xn such that their f value is maximum. So what we will do is, like, we'll decrease one variable, right? And we will increase the other. So suppose, so that the sum remains constant, obviously, because that is the condition, right? So suppose we are moving from x1, x2 to x1 minus a. Sorry, the razor really troubles me a lot. x1 minus a to x2 plus a, where this thing is positive still, right? So something is non-negative. So so this is something like this. Not just non-negative, positive, because you need to keep them positive for the argument to work basically. So yeah, so you're moving from this and keep all xi where I is 3 to n constant. So what can you say about the f value of this? So f of x1 minus x2, uh, okay, no. So what can you say about the x value of the new n tuple, where the first term is x1 minus a and the next term is x2 plus a, and the rest of the terms are the same? So you can write f of x1 minus a, f of x2 plus a, x3, x4, xn as something like this. Summation, sorry, not summation, f of x1, x2 up till xn plus. Okay, so suppose like x1 denotes x1 assigned to u and x2 assigned to v. Okay, then you can write something like this, right? Let's change the color. Okay, so you can write something like, so you have like, you are adding, so you will have terms of the form x 2 plus a into xw, right, where vw is an edge. This is how the summation is basically carried out, right? So you will have this thing plus an extra term a times vw edge xw, and similarly a term minus because of the x1 minus a thing, summation uw belongs to edge xw, right? And yeah, a factor. So I'll just write it up clean in the next page. Yeah. Any questions till now? Okay, this was a plus. Right. Feel free to ask any questions though. Uh, yeah, okay. Summation uw belongs to e xw. So this is what we found, right? So now you know that we assumed f of x1, x2 up till f of xn was maximal, right? What does that mean? So this implies that this term must be at most 0, otherwise f of this thing is greater than f of x1, x2. This would be a contradiction to maximality.
That you in the previous expression that you have added plus a times summation xw. So
Yeah.
where is v coming? I mean, what
Okay,
v
so
v?
like,
Where is v?
okay, so we assumed that x1 is the variable assigned to u, the vertex u, and x2 is the variable assigned to the vertex v. Okay,
Oh,
you're
okay.
assigning. Okay, so like there is a plus, so when you are like summing up, so you have like, you write something like x2 plus a times xw, where vw is an edge, right? So that is the plus a term.
So xw is simply another term like x. I mean,
Yeah, w is a vertex. We are assigning the real numbers to the vertices of the graph, right? So v was a vertex and you assigned x2 to the vertex v. So now these terms will come up if and only like xw will come if and only vw is an edge, right? So this is what we are writing basically.
okay.
Because, okay, uh, so this gives us that this term must be 0, sorry, at most 0, right? Which means so now a was non-negative, right? So you can just cancel out a. vw belongs to e, xw is at most summation xw, uw belongs to e. So this is what we got, right? Does anyone have any questions about how this we go from here to here? This is because of maximality. Okay, so now think about this thing. We did not use what's special about like x1 and x2. So you can like kind of see that this expression kind of prejudices u over v. something like that, right? Because u and v are kind of the same thing. Like they could be anything. Why should you have this sum greater than v? So you can basically repeat the same argument what we just did for x1 plus a, x2 minus a, and x3, x4 up till xn to get the exact opposite inequality. Do you get? This is basically symmetry. So like I could have just said hence by symmetry, but well, symmetry can mean a lot of things, so it wouldn't really make sense. Xw is at least summation uw belongs to e. Does this make sense? So these two will combine to give you summation of vw belongs to edge xw equals to summation uw belongs to edge xu. So now you can prove. So does everyone agree how I got this expression? If there are questions, please ask. So now if you like have this, now you can basically just prove this, right? So 0 x1 plus x2. We kind of, you can also like assume like uv is not an edge because we assume that in the beginning, right? So uv is not an edge because that is what we did kind of at the beginning. We assumed like uv is not an edge, so you don't have an x1 x2 term coming up if that's what you're thinking. So now you prove like f of 0, so this thing x3 x4 is equal to f of x1 x2 x3 and so on. So this is just write it out and expand sort of and use this. Okay, so yeah, so hence like smoothing, there's a theorem in smoothing which basically tells you if this happens, then uh, the equality case must hold for some number of xi equals uh, so like, so now when you are doing this, now how long can you do this smoothing process, right? Okay, no need of a theorem. How long can you do this smoothing process if you have something like, okay, continue this till there do not exist uv belongs to v such that uv does not belong to e and xu greater than 0 and xv greater than 0. So what you basically get is you kind of result in a clique, result in a clique, right? Do you feel how this works? So suppose something like, what is a clique? So clique, you have everything is connected to everything, right? So suppose the main you had a 5 clique, let's say. Okay, drawing a 5 clique is hard. Yeah, and suppose you are like u was here and v was here. So obviously, like if you have, what was the equality case we were thinking of? In the equality case we were thinking of, we had like equal values for all members of the clique, and we had 0 for all the members outside of the clique, right? So as notice that that is exactly what is happening here. So you have like uv is not an edge, right? Then you cannot, then if uv is not an edge, then like one of them will have like 0 and the other one is going to have a value of something like 1 by 5 in this case. So it works out. So the value works out, and final answer is k minus 1 by 2k by the similar logic as in the first proof where k is max click size in G. So does anyone have any questions regarding this? We completed problem 2. Anyone has any questions?
Only that part, that summation xw very equality case that.
Go on. Okay, how do I get this green box? Are you asking that? And why? Okay,
Yes,
so like,
yes.
okay, so first thing, our target is to prove that this holds, right? When you are going from x, y, okay, not this, or better this. this thing. I'm just using navy. Okay, you are trying to prove that this thing holds, right? But I just like use the blue border for. So our main target is to show that this operation is not going to decrease the f value. When you write it out, okay, so one way to do this is you start with a maximal x1, x2 up till xn, and you have to show that basically it doesn't decrease here, it's just equal, right? Because you can't go above the maximal value. So you have to basically show that if x1, x2 up till xn achieves maximal, then you can do a move of the form x2, xu, xv goes to 0, comma x2 plus xv, such that the value stays the same basically, right? So we assume that we assume that x1 and x2 were like x1 represented vertex u and x2 represented vertex v, right? And we assumed uv wasn't an edge. What we did was we tried to smooth, we decreased the value of x1 and increased the value of x2 so that the sum was the same. Okay, then what we did was like, so we calculated the value of fx1 minus a and fx1 minus a comma x2 plus a, and remained, and all the other n minus 2 variables were the same. Okay, when we did this for x1 minus a and x2 plus a, we found that we had f of x, x1 comma x2 up till xn term plus some other fringe terms, right? So now you know that you are adding something with f of x1 plus x2 plus up till xn, right? You know that this f value of x1 x2 up till xn is maximum because that is assumption, right? This is maximum, right? This is assumption. So this entire term, like a times vw belongs to edge xw minus a times uw belongs to edge xw, must be less than 0, because if you're adding positive stuff to something that is already maximal, you get something more maximal. That is a contradiction, right? So this gives you an inequality. So this gives you this inequality basically. Okay, but now note that this inequality is kind of more sort of prejudiced towards u than towards v, right? You are basically, it's claiming that some sum of u, some function of u is greater than some function of v. But note that v are, u and v are like not very different from each other. Like, okay, like think about it like this, like one could have mapped to v instead, and you two could have mapped to u instead, and why should anything change, right? So in other words, u and v should have like same sort of priorities. Like if you are having an equation, you shouldn't discriminate between u and v in some way. So like what you can do is basically you can just like redo the argument for, okay, where is it? Yeah, x1 plus a, x2 minus a, and all the other variables constant. When you do this for x1 plus a and x2 minus a, what happens is like, look at this expression. This term will become a minus and this term will become a plus. And the resultant term should still be at most 0, because otherwise you are adding positive stuff to maximum, right? So what you gained is like, then this inequality is going to hold true. So like you get something like a at most b and a at least b. So a must equal b. So that is what is happening here. So does that make sense? Is that a bit clearer now? He didn't get disconnected, right? Am I audible?
You are, yeah, you're audible.
Okay, okay. So the person who asked the question, I hope it is fine now. So if there are no more questions, I'll move on to the next
Yes, yes,
problem.
yes.
Okay, okay. It's good, right? Then I'll move on. Okay, so next problem is,
Yeah, yeah.
okay. Okay, might run out of battery actually. Uh, yeah, so it's a candy problem. So 1.3. So you are given some number of candy colors and 2n candies of each color. Every kid takes 2 candies of pairwise different color. Every k plus 1 kids, at least 2 have, okay, like this. There are 2. Uh, there are two having the same candy color for at least one candy. So find max number of children. So for this problem, obviously you have to start by guessing the answer, right? So anyone did anyone guess the answer for this? So one way to do this is always take small cases, right? So how do you do about small cases? So suppose n was 1 and k was 1, right? So among any two children, you will have like one of them have the same color. So something like if you start with C1 and C2, right? So person 2 will have one color in common with person 1. So let that color be C2 and suppose another color is C3. So think about person 3. Person 3 is going to have like um, what? A color common with C1, a color common with this is person 1, person 2, person 3. So person 3 is going to have a color common with person 1 and a color common with person 2, but it cannot be C2 because a number of candies of C2 is only 2 and that has already been exhausted, right? So person 3 can have something like C3 C1. Does everyone agree with this construction? Hello. Does everyone agree with the construction for the trivial case?
Yeah, yeah.
Okay, so now let's like do, I think, sorry, not n equals 1 still. Where is it? N equals 1 and k equals 2. Yeah. So for now, you can have something like every three people, one of them has common, right? So you can have like C1, C2, C3, C4 because three people. So now when you're adding in the third people, let's say it has something in common with C1. So you're writing C1 and C5, right? So when you are like, now you are introducing the fourth people. So for fourth, if you like, this is something like you have to do it yourself, kind of. It's like hard to explain how I'm working the case out, but you see something like this happens when you are trying to solve for this case, right? This is something you should do yourself because small cases are something you must always do for a problem. This gives you a hint about the answer. So you find that something like, so any guesses for the answer now? For this the answer was 3 because if you add anything you are out of options, and for this also the answer is 6. If you add anything else you're out of options. You can just check for yourself. So from these two cases, does anyone have any guess for an answer? Oh god, what happened? Sorry, something just dropped.
3k.
EK.
Come again. Should be dependent on n, right? N is not completely useless. So someone said 3kn. That
3km.
is, yeah, that is the right answer. Yeah. So this is why equality is very important for extremal graph theory. You need to know the answer before you are trying to prove at least. And if you cannot find out the answer, sometimes difficult graph theory problems will make it hard for you to even understand what the equality structure is. In those cases, well, honestly, it kind of sucks. It's kind of hard to solve the problem then. So answer is, we'll see a couple of problems of that kind as well. Answer is 3kn. So now suppose we're trying to interpret this in terms of graph theory, right? So what would be a good interpretation for this? So what we are going to do is we'll assume like let color of candies be vertices, right? And what does a child represent? You will draw an edge UV if some child takes candy of color U and candy of color V. Okay, so childs are basically edges. Okay, so this is our how to review it in kind of in terms of a graph, right? So what are the conditions you are given? Okay, first of all, let us just draw the equality case. Let's not worry about just solving the problem yet. About the details first. Let's first find the equality case. So what is the equality case for this? It is just like triangles. I think the equality case for this should be 3kn triangle. I think it should be kn triangles or something like that. Give me a second. Uh, yeah, I just like forgot what the equality case was. Give me a second. Yeah, so yeah, kind of stupid. You can just like maybe n equals to 2 basically tells you a bit more. You can do the n equals, okay. You can kind of do the n equals 2 and k equals 1 case as well, then it becomes much more obvious. So yeah, suppose like I'll just mention the conditions one, it becomes easier to view it then. So like you are given, suppose you view the candies as colors and the children as edges, right? So what you happens is like you can think of it like this, like every vertex should have degree at most 2n because there are at most 2n color candies. Also the resulting graph G is possibly multiple, is possibly a multigraph. What is a multigraph? It might have like more than one edges between two vertices. Multigraph, sorry. And what will be the construction for 3kn? That will be just you take uh, k triangles, right? And every edge of the triangle has multiplicity n. Okay, does this make sense? So do you see how we have 3kn? So we have uh, suppose we have k triangles, each one of them has like three edges and every edge is multiplicity of n, so that gives you 3kn. Does this make sense? Why multiplicity of n makes sense? Does that do people see? Because every vertex has degree at most 2n, right? And multiple edges allowed. Multigraph means multiple edges between vertices allowed. Vertices allowed. So this is how you get the 3kn bound. So now if no one has a problem, I'll just move on to the next page and I'll try to prove the bound. Does anyone have any question? Okay. So now we are moving to the proof of bound part. So how to interpret the k plus 1 condition? Does anyone have any ideas how to interpret the k plus 1 children condition? Okay, so I'll define a term. I'll call the term matching. So what is a matching? A matching is a bunch of, it is a subgraph. Okay. A matching is a subgraph of any given graph G, not necessarily the one in the problem, okay? Such that it consists of a pair, it consists of a bunch of disjoint edges. What do I mean by that? Something like if you have a graph of the form. So if you just consider this subgraph, right? This is a matching. Okay. Does everyone understand what I mean by the definition of matching? So now, if there are no problems, I'll just move on. Okay. So now I'll discuss a thing that is called maximal matching. What is a maximal matching? It is the matching with max number of edges. So we defined matching as a subgraph which just had a bunch of disjoint edges. Okay. So now if you consider the subgraph which has the maximum number of edges, we will call it the maximum match. We'll call it the maximal matching. Suppose this is a maximal matching for a graph and you have some other vertices which are not a part of the graph. Now think what happens. So suppose you call this part of the graph the M, the matching, and this part of the graph you call it, say, give it a name, like call it N, let's say, which is N is just the graph, okay, the vertex set minus the matching. Okay. So now think about it. Suppose you take M to be maximal. Okay. Then M has the maximal number of edges possible in a matching. Right. So what happens if there is an edge between two vertices of N? So then you could have just dragged this edge into M, right? And then you could have increased the size of the maximal matching. That would have been a contradiction, right? So we come to the conclusion that N cannot have any. Is there a question?
No, I think I unmuted myself by mistake.
Okay, cool, cool. N cannot have any edges to itself, which implies that N is an independent set. So this is a very important property of a maximal matching. What happens if you focus on a maximal matching, right? Then the other part of the graph must necessarily be an independent set. If it is not an independent set, then you can find an edge inside the other part of the graph, and you can just add that edge to the graph M. Sorry, to the subgraph M, which is the maximal matching, right? And you can just increase the size of the maximal matching, which would be a contradiction, right? So this is a very important property. Take note of this. Maximal matching is like often useful for dealing with independent sets. Max matching. Okay, my handwriting is going haywire. Useful for dealing with independent sets. I'll tell you why I'm talking about maximal matching. Okay, so now can you interpret the problem condition in terms of maximal matching? Anyone? I think I'll probably take like some time after the 90-minute mark. I want to discuss like 3 problems after this. Okay, let's see. I think I'll take some time. I hope that is okay. Okay, yeah. Can someone like describe the problem condition? The problem condition was if you take any k+1 edges, if you take any k+1 edges, then you will find a candy color of the same. You'll find like 2 of the edges share a candy color. So what does that mean in terms of maximal matching? Can we say this? Can you say this? Does everyone agree that this is the condition basically in graph theoretic terms? Are there any questions? So what happens is like I'm claiming that the k+1 condition is equivalent to having a maximal matching of size at most k. What I mean is like if suppose this were not true, if the maximal matching had k+1 edges, right? Suppose the maximal matching had suppose k was 3 and maximal matching had 4 edges in the graph we are building, right? So what would happen? So these are like 4 children, right? These edges, but these 4 children you cannot find 2 of them such that they have a candy color in common, so this would violate, right? So does everyone agree that this is basically the k+1 condition written down in graph theory terms, that the maximal matching must be of length at most k? I'll just go on. Please do ask if you have any questions. Okay, so moving on. So obviously now the obvious course of action is take maximal matching M and do something with it. Okay, and do something with it, right? So suppose the maximum matching was x1 to y1, x2 to y2, and so on up till say xk to yk. Actually, the maximal matching can be of size less than k, but for our purposes, we can just assume it is of size k because, well, you are adding somewhat more edges, right? So you cannot like do harm or something like that. The more the like you cannot, like if you have more number of edges, you cannot have harm unless it's like at least at most k. So yeah, so now we'll discuss some properties about the structure of maximal matching. So now also one important thing. So suppose the rest of the graph is like here. Okay, so suppose this is the rest of the graph. This was n and this is m. Okay. So note that first of all we discussed that n is independent, right? No edges from n to n, right? So if n is a vertex in n, right? So all edges in n, all edges coming from n are incident on some vertex of m. Do you understand this? Because suppose you have an n here, right? So you want to like sort of have edges from n, but you cannot have edges from n to some other vertex in this set, right? In the goal set. So what you will do is you'll have to be like neighbors with some vertex of the maximal matching. What I mean by adjacent is like I'll say an edge is adjacent to u if like u is one of the endpoints of it. So u adjacent, if v means uv is an edge for some v. Right. So I hope what the meaning of adjacent is clear. So this basically tells you that all edges of G are incident to some vertex in M. Right. So basically all edges of G are incident to some vertex in M. So this is an interesting property. Actually, I'll use this term if I can discuss another problem later. So there's another definition actually. So if you have a set of vertices such that uh, all edges, a set of vertices S such that all edges have at least one endpoint in S, then you call S a vertex cover. This is the definition sort of. Okay. So this basically, this property tells you is that maximal matching is always a vertex cover because the rest of the graph is an independent set. So now think about this. Okay, so suppose A and B is AB is an edge of M, right? So what are the edges that can come out from A or that can come out from B? So suppose this was N. So there are some edges that can go from A to N, say, and some edges that can go to A to U, suppose, where U also belongs in M, right? So these are the two kinds of edges that can go out from any vertex in M, right? So you will call this edges as a traitor edge, let's say. Let's give it a nice name, traitor edge, and we'll call this a patriotic edge. What I mean by, okay, like obviously you can have, okay, because these are only the only two kinds of vertices, only two kinds of edges that can have you can have from the vertices, right? Because patriotic because it remains inside M sort of, and traitor because it goes outside M. Okay, so now the idea is like you have to think sort of how to think about patriotic edges. So suppose something like this happens. Suppose A and AB belongs to the maximal matching, and something like this happens that there exists a U and V in N such that something like this happens. So suppose AU is an edge and BV is an edge. So we claim that this is a problem. Why? Because suppose like your matching, your maximal matching had the edges AU and BV instead. Right. Suppose you took these two edges instead of this one. Then you are increasing the number of edges, but you still have the maximal match and you still have like the matching property, right? So this would contradict maximality. So this cannot happen, right? So what this means is if A is adjacent to U for some U belongs to N, then B must also be adjacent to like U, right? So in other words, how many edges can be there? So how many traitor edges can be there from like one edge AB belonging to an M? 2n, right? Because they can only be ever adjacent to one common neighbor of A comma B, right? And that common neighbor has been already prescribed to have a degree of at most 2n. So do you agree that so at most 2n traitor edges from every edge in, I don't know what is the name, from every edge in from every edge, so let's say AB in M. Does everyone agree till here? If anyone has a problem, please ask. Okay. Okay, let's move on then. So now think about it. So we found that all vertices, so not all vertices, all edges give out a max of 2n traitor edges, right? So now look at, I'll just use black. Look at sum of degrees of vertices in M. So there are 2k vertices and each one of them have degree 2n at most. So this is like they have at most 4kn is the degree, right? So now what is sum of degrees of vertices in M? So you are counting, so suppose this was M, right? And this was N. So you are counting edges of this form, call this the type 1 edge, type 1 edge, and you are counting an edge of this form M to M, call this a type 2 edge. Okay, so you are counting M to N edges once plus the M to M edges, you are counting it twice, right? Because if you have an edge UV inside M, right, inside M does not like necessarily mean it must be a part of this maximal matching. Okay, so something like if you have something like let's say AB and CD are edges of the maximal matching, then A to D, suppose A to D was also an edge. Okay, it is not a part of the maximal matching, but it is the edge in the original graph. Okay, then A to D is still an M to M edge, right? Because A is a part of M and D is a part of M. So it's 2 times M to M edges. Now you know how many M to N edges are there. We understood that every edge gives out at most 2n M to N edges, which M to N edges is basically a treated edge, right? So every edge gives out a maximum of 2n M to N edges, and so there are 2 k edges, right, in M. So this is at most 2n, right? So how many M to M edges are there? That is just 4nk minus 2nk by 2. So total answer is 2nk plus 3nk plus just nk. This is just nk, right? It's 3nk. So yeah, anyone has any questions? This was a good problem. This was a China problem, TST3 kind of. So it was supposed to be hard. Does anyone have any questions? Just check the chat.
No, it's fine.
Okay, yeah, then let's continue. So next problem I want to discuss is where I go. Yeah, let's discuss the amicable pairs problem later. That is like more algebraic. I want to discuss the others first. Let's move to problem 1.5. That is, you are given a function f belongs to x, where x is the set of first 100 positive integers. Okay, so you are given for all subsets A with size 40, you have AFA is not 0 and fx is not equal to x for all x belongs to A, or for all x belongs to x. Okay, so find minimal k such that there exists subset B belongs to X, such that if B is K, then B union of FB is X. So did anyone get this problem? So do you do understand what f of A means, right? F of A is basically the set FA where A is some element of. Okay. So basically this problem tells, so I'll try to present two solutions to this problem. The first one was how I came up with it, how I solved the problem. The second one is probably a much better way to think about the problem. So this one of the solutions is stupid, one of the solutions is smart. So, okay, let's begin. So you do understand the problem statement, right? So it tells you basically whenever you have a set of size at least 40, right? You are ending up with an intersection between the image. So obviously you can think of the graph so you can obviously draw a graph where the vertices are just elements of X, sorry. Right, so you can draw a directed graph actually. So you can draw a graph U is directed edge towards V if f of U equals V. Right, this makes sense, right? We are just drawing a directed graph. So, okay, so now how I solved this problem was actually in this problem, I think all of the process I've seen, you find the construction after solving the problem. So I'll show you my solution first, which might seem a bit unnatural, but I'll try to explain it as much as possible. Okay, so the problem tells you that you have A times FA is not zero, like they have non-trivial intersection whenever A has size 40, right? So what I will do is I'll pick S belongs to X such that S times f of S is equal to 5. Okay. What am I doing here? I'm picking a subset S of X such that the intersection of the S with its image is is like there is no intersection, is 5. Okay, there is no intersection. We know that if if like S has size 40, then there must be intersection, right? So I'll pick S belongs to S, and also you will always picking extremally, right? So you will pick mod S to be maximal. Right. So this basically directly tells you that mod x is at most 39 because if you hit 40, then you will have an intersection, right? Also, what if there are multiple such? Then just pick the one with maximal fs. Why are we doing this? Why are we picking maximal fs? So note that these are like if you have like when you are trying to deal with s, if you take s maximal, that will already impose a lot of restrictions on the other elements. So like when we are taking fs to be maximal as well, right? So we are since they are disjoint sets, so you have like a lot of control over more elements. So this is one way I think about it. So this is one way which why I picked this kind of a consideration. So let f of s denote the set T, right? So suppose this was S and this was T, and there is some part of X not covered by S and T. Suppose that part is U, and U equals to X set minus S union T. Okay. So now what we will do is kind of play with the structure. We have a lot of restrictions because of the conditions imposed. So something like S is maximal such that S intersection its image is 5. So if you add even one element to S, right, the resulting set will have image have some intersection with its image. So there is something will like really use. So this is kind of like throw stones in the dark solution. Okay. So suppose you consider an element U belongs to U, such that okay, so just consider an element U belongs to U. So what can you say about f of U? So suppose this was U here. Okay. So suppose U pointed to somewhere here or somewhere here, right? And or it can point to somewhere in S. Suppose it points to somewhere here or somewhere here. In other words, suppose fu is not inside S, right? Then what you can do is you can kind of inculcate U inside S, consider, right? Then what is Fs? Fs is obviously Fs dash, sorry. Fs dash is basically just T union F of U. But note that this is disjoint from S by our assumption. Disjoint. Right. So what we found is like if you have a U belongs to U such that its like image is not inside this set S, then what we can say is like you can sort of increase the size of S. You can just add that element to S and still keep the like this condition to be true, right? And increase the size of S. So this contradicts maximality of S. Right. So what does that mean? So basically, we came to the conclusion that Fu belongs to S for all U belongs to U. Does that make sense? Does everyone understand the proof of this? If there are questions, please feel free to ask. Are there any questions? Okay, let's move on if there are no questions. So now if you like play around with the structure a bit, you found that U's elements, right, are restricted to be inside S. Suppose this was S. So now can something like this happen? Like suppose you have U1 here and U2 here, and they are pointing towards the same element S. Can this happen? Think about it. Does anyone see a problem with this, or is this fine? Anyone having any ideas about this case? Okay, so I'll just tell you how to think about it. So now think about like this. Suppose this, if this was true, right? U1 and U2 are both pointing towards the same element. So suppose F U1 equals F U2 equals S, right? So what happens is like you can think of the structure in this way now. Suppose you swap out S and add in U1 and U2, right? So then the graph would look something like this. So not they're the same elements. Suppose you add U1, U2 in S and get S in the outside of S. So do something like S to S bar U, S bar S, union of U1 comma U2. So swap out S for U1. S dash still has S dash union, sorry, intersection of Fs dash is phi, and mod S dash is greater than S. So this again is a contradiction to maximality of. So this can't happen. So does everyone understand what I mean? What I mean to say? So like if you have, so if you want, so suppose if you enumerate the elements of U, right? Suppose are the elements of, then let's say Si are unique. Does everyone follow to this point? If there are any questions, please feel free to ask. Okay then.
Can you
Moving
please
on.
explain again from
Yeah.
the line
Okay.
resulting set S dash?
Okay. 1 second. Can you come again?
Uh, can you just repeat from the point where you wrote swap out S, because I think you
Okay.
froze
Okay.
at
Okay.
that time.
Oh, I'm sorry then. Okay, so what happened is like suppose you have these edges U1 and U2 both pointing towards S, right? So what you do is you swap out small s from the capital S set and add in U1 and U2 instead. Okay. So note what happens. You are increasing the cardinality of the set S, right? Suppose the new set is S dash, which now has U1 and U2 in place of small s. Then the new set S dash has more cardinality than S, but it still satisfies this condition, right? This condition is still satisfied. What does that mean? You now reached a new set S dash such that it still satisfies the intersection is equal to 0 condition, and it has more cardinality than S. We assume S to have maximal cardinality. So this is a contradiction to the maximality of S. So this means that you cannot have this situation. So this cannot actually happen. So U1 and U2 cannot point to the same element as. So this means like if F is sort of F, like if you like write out the elements of U as U1, U2 up till UN for some n, then you have, if you write F of U1 equals to SI, then SI must be unique. So this is what the claim tells us. Does that make sense now?
Yeah, thank you.
Okay, cool. So now, okay, so we are quite close now. So suppose something, let's say you have something like, think about it, like we took F of S to be maximal as well, right? If there were a lot of S. So what does this tell you? Lot of elements in image, basically. So if a lot of things point towards the same element, have same image, it's bad for maximality, right? What I mean, suppose bad for maximality. So suppose you had like okay, yeah. So suppose you had like so someone in U going to ST1 and then someone in S2 going to so suppose you had like this was S and this was T. So suppose you had a guy S going to somewhere in T and a guy here going to here and a guy going to here as well. Okay, screwed up. Sorry. Yeah. Suppose you had a guy going to here as well. So this is bad for maximality, right? Because 1 and 3 basically have the same image here, right? If they had different images, that would probably have been nice for maximality of T, right? So this is one idea we are going to use here. So suppose something like this happens. Suppose U1 is going to S1 and U2 is going to S2. And suppose they point to the same element T, right? Can this happen? Now, does anyone see any problem with this? Okay, so think about it like this. So we will always try to increase Fs, right? Okay. So think about it like this. S1 is not adding anything new, or S2 is not adding anything new. If S1 was already present inside S, right, S2 is not adding any new element to Fs, right? So what we can do is we can swap out S2 for U2. See how this works. So we had initially something like, oh God, okay, yeah. Suppose you had initially something like U1 going to S1, going to T, and U2 going to S2, going to T. This was your S. Now suppose you have this, S1 goes to T, U2 goes to S. Suppose this is your new S now, and you had like other elements of S as well. Do you understand what I am doing? Suppose call this S dash, right? So what we did was we swapped out S2 for S1, right? Sorry, we swapped out S2 for U2. So what this does is like S dash has the same cardinality as S, and S cap Fs, S dash cap Fs dash is still phi, right? Because S2 is not, because now S2 is out of the new set, right? But what's new? F of S dash has a cardinality more then has cardinality more than f of s. So this is again a contradiction. You get what I mean? So what this implies? So this implies that even the FSIs will have like different okay, so this means SIs have greater cardinality. Sorry, what am I saying? SIs point to unique elements. Does everyone understand this? How this happens? Is the proof clear? Okay, I'll just proceed as I'm sort of time anyway. I'll have to.
Can you explain the last line again?
Okay, so what what did we assume? We assumed if possible, suppose S1 and S2 both point to T, where U1 and U2 are pointing to S1 and S2 respectively. What we did was we built a new set S dash where we swapped out S2 for U2. Okay, what this does is the new set S dash still fulfills the intersection with image equals to phi condition. Okay, and but what is different for S dash is that if you look at its image has the S2 element extra than the image of Fs, right? So you basically increase the F value, the F of S dash, the image, the size of the image of S dash. But we had already taken F of S to be maximal. Okay, so this poses a
Okay.
problem.
Okay.
So basically, what you saw is like, so if you have like a U1 in U, I in U, you can find a Ti in T by something like Ui goes to Si goes to Ti, right? So this directly implies that there is, so basically there is an injective function. So f acts like an injective function between U and T, right? So this directly implies that T is at most U, T is at least U, right? So this is basically because f acts as injective between U to S and S to U, S to T, or F square is better probably. Okay, so if you knew that S was always this, so this implies that T plus U was at least what 100 minus 39, that is 61, right? But you know that this also holds, so this implies that T is at least 31. Yeah, yeah. So now look at what we have achieved, right? We had come to the conclusion that if this was U, this was S, this is T, then everything from U goes to here, and people from here go to here. Okay. But note that if you consider S union U, okay, that is bad. I'll just okay. I hope this is understandable though. Suppose you consider S union U, okay. This suppose you name this set as B. Note that B in union of FB must be the entire set X, right? Because then because S of F of B, F of S is just T. So you are spanning the entire set basically using B union FB. Do you understand why this is true? So, but now basically
Yes.
this was B. So now B, what is B? Mod B is basically, since U and S are disjoint, it is just S plus U. Okay, so that is at most 100 minus T, which is just 100 minus 31, that is 69. So we came to the conclusion that K is at most 69. Now, what about the proof of, what about the construction? As usual, for the construction, we'll just appeal to whatever bounds we used and we'll plug in the equality cases. So suppose you will have a U1 here, which goes to S1, right? No, recall that for the equality case, you have mod S equals 39, mod U equals 30, and mod T equals 31. Okay, so you have a U1 goes to S1, S1 goes to T1, okay, and 30 times this, right? And what about the remaining nine elements of S? Suppose S31, S32, etc. Suppose you are having S31 up till S39. Okay. Yeah. So they only have one element in T, that is T31 to map to, right? So all of them will map to T31, 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 T31. But what will T31 map to? We can just assume that T31 maps to S39 and be happy. And similarly for this, you need to have an edge from T1, right? So you just do the edge T1 to U1. Does this make sense? So finally, we end up with 30 triangles, one something like this, something like this. That is the S39 and T31, okay? And 8 others and something like 8 others all pointing towards. This is S31, S32 up till S38. This was your T31. This was your S39. And this is basically SI to UI to, sorry, UI to SI to TI and TI back to UI. Okay. So any questions regarding this proof? If there are no questions, I'll present another proof of this, which is probably better, I think, in some ways. So another proof. So think about it, right? So like, what does the condition B union FB equals to phi even imply? This basically tells you that B forms a vertex cover. We defined vertex cover in the last section. Vertex cover is any set such that all the edges of the graph is incident to at least one edge, incident to at least one vertex in the set S. Forms a vertex cover of G. G is the digraph induced by the function f. So the problem asks for largest value of minimal vertex cover. How do you interpret the condition like A union FA equals to 40? Sorry, A union FA equals to is not A intersection FA is not phi if A is at least if A's cardinality is 40. This basically tells you that independence if okay vertex cover given maximum value of maximum size. Okay. Size of in-depth set is 39. Does this formulation make sense? Does anyone have any questions regarding this formulation? Do you understand why this is like makes sense? So now how to prove this? I'll just assume like everyone has no questions since no one is asking any. I'll just go over it again. So we understand that B forms a vertex cover of G by the condition, right? Also, you are given like the condition S intersection Fs equals phi if and only if implies mod is at most 13 implies S. So this is an independent set, right? S is independent because it doesn't have any image, any U to V vertices where U and V are both S. So S at most 39 implies like max size of in-depth set is 39. Okay. So since we are dealing with vertex covers, right? Since we are dealing with vertex covers, what's a good way to think about vertex covers? We just did it in the last example, right? So take maximal matching. Okay. So if you take a maximal matching, suppose this is a maximal matching. Okay, and suppose this is the other part, call this N once again. Suppose these are vertices here. Okay, so suppose there are M edges in the max matching. So obviously N has 100 minus 2M vertices. Right. Now, again, like, think about it. Yeah. So like, again, note that since n is independent due to maximality of m. Right, so I'll just change the page. So what does this imply? Like mod n is at most 39. So this implies like 100 minus 2m is at most 39, which implies 2m is at least, I think this implies 2m is at least 61, which implies m is at least 31, because m greater than 30.5 doesn't make sense. It's an integer, right? So m greater than 31. So now, how to form vertex cover? Note that vertex cover is a bit tricky here because the edges are directed, right? So you can't just take like all the vertices of M, right? Because you have edges of the form something like this, right? Or edges of the form something like this. Yeah, edges of the form something like this. So how to form the vertex cover? This is actually easy. So suppose M was of the form xi to yi, right? Where suppose this was x1 to y1, x2 to y2, and so on up till xm to ym, right? So then take the vertex cover B to be all the xi's union of n. Okay, convince yourself that this works. Convince yourself this works. Right. So this B is a vertex cover, and also you note that V has like size 39. Okay, B has like size I think 100 minus 2m plus m, which is 100 minus m, which is at most 69. Yeah. So that proves the problem. Does anyone have any questions with this proof? Feel free to ask.
Yeah, can you please explain from when you like B equals the sequence VI union N?
Okay. So how are the edges inside the maximal matching? So the maximal matching is this, right? Suppose the maximal matching is, this is x1, y1, x2, y, xm, ym. So suppose it was an undirected graph. Okay, if it was an undirected graph, you could have just chosen the vertex cover to be x1, y1, x2, y2 up till xm, ym, because you know that the rest is an independent set. So the all the edges will have at least one endpoint in some xi or some yi, right? But this is a bit tricky. This is a digraph, right? So directed graph, right? So this, if this was m, so you can have edges of the form this, right? So now if you take this edge, when we mean vertex cover here, we actually mean to say that the endpoint of edges, like not on the sort of receiving end of an arrow, you need to be on the giving end of an arrow. Okay, so if that was if you didn't already like okay guess that. So when we mean vertex cover here, we just don't mean like adjacent to an edge, we mean like the edge should be like nice, right? You cannot be taking arrows, you have to be giving out arrows. So if you just take x1 y1, right? So this kind of an edge is going to cause a problem. So what we do instead, we will take the entire n, okay, and you will take just this. So if you take x1 up till xm, then these edges are getting covered, and also these kind of an edges are getting covered, right? And if you take n, then these edges are getting covered. Okay, makes sense?
Yeah, thank you.
Okay. I think we are out of time. I kind of wanted to discuss 3 more problems today. I think I'll probably write some walkthroughs for them. Okay, then does anyone have any questions from the session in general?
I have a question from last class.
Okay, go on.
So like in the proof of Mantel's theorem where we proved that less than or equal to n square by 4,
हाँ
तो उसके अंदर like we considered that u be a vertex of maximal degree, like u and v were the vertices that were given, I think.
for first proof or the second proof?
The first proof.
Okay, no, UV was just an edge, any edge.
Okay, okay.
So like it proved like if you have UV as an edge, like you cannot have a common neighbor of UV, right? That would just result in a triangle, right? So if you look at the neighborhood spanned by U and V, okay, these two neighborhoods have to be disjoint. Now you see that if this condition is not satisfied, then there must be an intersection. Okay, if this is not satisfied, so the negation of this results in an intersection here. So we found this for any edge, right, is at most n. If UV edge, then this holds, and then we summed over all UV edge. Yeah.
Okay. Okay.
Okay then. Bye, I guess.
Bye. Wait, okay, I'll end the recording. Um,